Hello, everybody. So today we're going to be talking about propositional logic, basically. We're going to be talking a lot about entailment and what sentences are true, when they're true, and conjunctive normal form. So to start off with, I want to talk a little bit about the difference between entailment and implication, because I think that comes up a lot. I think it's like confusing for a lot of students because they are really similar concepts, but they're also importantly different. So to illustrate this, I'm going to talk about two different sentences. Sentence one is I ate beans for dinner, and sentence two is I am 5'8", right? These are both sentences that can be true or false of a world. And in fact, in this world, they're both true. I actually did eat beans for dinner today, and I actually am 5'8". So let's look at the difference between implication and entailment by first thinking about implication. So isn't the case that I ate beans for dinner implies I'm 5'8" inches? Well, that's sort of like implication is a fact about a certain world, right? So to think about this, like remember that A implies B is just the same thing. You can think of it as just shorthand for not A or B. Like either the first thing is false, or if the first thing is true, the second thing better also be true. And so in this world, I ate beans for dinner. Well, it's not false, but I am 5'8" is actually true. So what that means is that in this world, I ate beans for dinner implies I'm 5'8". So this is big tick. And that's because this statement is about a particular world. Particular world. Or a model is what it's sometimes called. In contrast, let's look at the entailment. So does I ate beans for dinner entail I'm 5'8"? And it doesn't. And to see why, what entailment is entailment is a statement about all the possible worlds, right? So this, that's not a good circle. This circle here is going to represent all possible worlds. And let's say this circle is like going to represent the worlds WORLDS, where alpha is true, right? So alpha is just some sentence. I've drawn you all the worlds where alpha is true. And this slightly bigger circle here, this green circle, is going to be all the worlds. They're not really circles, but that's fine. All the worlds where beta is true. So here, what we see is that the orange circle is totally inside the green circle. So what that means is that alpha entails beta. That's totally correct. That's what alpha entails beta means. It means that like in all of the possible worlds where alpha is true, beta is also true. However, if we change this a bit so that it were like this type of situation, right? Then it would no longer be the case that alpha entails beta, because there would be some worlds where alpha was true, but beta was not true, right? Like these worlds, it would mess up in. So that gives you a sense of the difference between entailment and implication. And I'll just write at the top some things you can do with entailment. So firstly, alpha entails beta if and only if alpha and not beta is unsatisfiable. So by unsatisfiable, I mean there's no world in which alpha and not beta is the case. And to see that like in this diagram that I have right here, you can see like here's one world in which alpha and not beta is unsatisfiable. So alpha does not actually entail beta. But if we change it a little, and let's redraw all the orange, and we'll redraw the green circle to be bigger. This time, you can't actually find any world where alpha and not beta is true, because all the worlds where alpha is true, beta is also true, right? Like here, here, here. So that's the first thing to note. The second thing to note is that alpha entails beta. That's true if and only if alpha implies beta is valid. And what do I mean by valid? I guess that word has a lot of meanings, but in this case, I mean true in all possible worlds, or like something that you can prove from no assumptions, just like definitely true. And the way to see that is like in this case, alpha implies beta is valid. Because if you look at like all these possible worlds, right? Like all of the ones where alpha is true, beta is also true. And that's what you need for alpha implies beta. But if we change the green circle to be like this, then here, right, we've got a point where alpha implies beta isn't true. Therefore, alpha implies beta isn't actually valid. So hopefully that gives you a sense of the difference between entailment and implication. All right, so let's get on to question 1. All right, so we're providing justification for whether each of the following are correct or incorrect. So the first is X or Y entails Y. Is that correct or incorrect? The answer is, this is incorrect. It's not true. Why isn't it true? Well, I'm going to draw you a possible world. And basically in this possible world, we're going to have X or Y, but we're not going to have Y. And the possible world is pretty simple. It's a world where X is true and Y is false. And to be clear, that like when we're talking about propositional logic, that this is what we mean by possible worlds. We just take our like atomic predicates, like X or Y, and we say whether they're true or false. So in this world, X or Y is true because X is true, but Y is false, right? We just said it was false. So we found a world in which this part, in which this part it was true, but this part was false. So that means that the entailment doesn't hold. So that's a big no. All right. Now let's look at this kind of more complicated one. The thing we have to check is whether or not X or Y and Z entails X implies Y. So what we're going to do is we're going to do the satisfiability check. So we're going to form this sentence that is the left-hand side of the entailment. So that's, we'll zoom in to give ourselves more space. So that's not X or Y and Z, and not X implies Y. And we're going to try to see if that's satisfiable or not. To make it a little bit easier for ourselves, we'll replace X implies Y by the thing that it just actually means. So X implies Y, that is just the same thing as not X or Y, right? That's just like, these are just like the same expression. That's like how we defined X implies Y, basically. Right, so we've simplified it a little bit. Now what we want to do is we want to simplify not X or Y. So we have these rules for how we bring in this negation symbol. So the way we do it is not of not X. That's just X. So we're done with this part. So I'll underline it. Now we're onto the or. When you have not of an or expression, the or gets turned into an and. So we'll turn this into an and. So now we've done this part. And now when the not hits the y, basically it becomes not y. Now we've done this whole expression, so we can delete this not out the front. So here's our new, here's our new expression that we're looking at. Not x or y and z, and x and not y. And we're going to see if we can satisfy this. Well, in order to satisfy this, right, because of this one, x needs to be true. And because of this one, y needs to be false. Because otherwise, because of this and right here, right, we've got to have like x to be true and not y to be true. And this is actually why we did the whole massaging, so we could get like the and of a bunch of stuff. Okay, so suppose x is true. Well, that means that this is false, right? Because if x is true, then not x is false. And because y is false, let's stick with red. Because y is false, y and z is also false, right? Because for y and z to be true, y has to be true, and also z has to be true, but y is false. So what that means is that if we satisfy the right-hand side of this conjunction, we can't also satisfy the left-hand side. So our sentence was, so just to to remind people, our sentence was not x or y and z, and also not x implies y. That is unsatisfiable. And what that means is that the entailment, this guy, is true. So that's a big tick. So hopefully that gives you a sense of what it's like to sort of reason about unsatisfiability of like the thing on the left and the negation of the thing on the right. So next we're going to use our other trick that we mentioned to think about the implication. So this is x or y, and z or not y entails x or z, and we have to figure out if that's true or not. So let's think about the implication here. So what that is x or y, and z or not y entail that. No, we're thinking about implies x or z. And we want to figure out if this is true in every possible world. Well, we can sort of imagine that this instead says alpha implies beta. So for this to be false, this is only false if alpha is true and beta is false, right? So because alpha implies beta, that's a promise. It's basically saying, look, as long as alpha is true, beta is false. So the only way you can break the promise is if alpha really was true, but you didn't give me beta. All right, so x or z, in order for this to possibly be false, right, x or z would have to be false. So what that means is that x is false and z is false. But now let's look here, right? Because x is false and z is false, this thing is the same as false or y and false or not y. So if y is true, then this side has got to be false, because false is false and not y is going to be false if y is true. And well, if y is false, then this side has got to be false, right? Because here it is, y, but we just said it was false. So false or y has got to be false. So what that means is that this implication here, the only way we could make this left-hand side, this right-hand side false, also made this left-hand side false. So what that means is that the implication is always true. We can't come up with any situation where the implication is false. And because the implication is always true, that means that the entailment is true. It really is the case that whenever x or y and z or not y, we also have x or z. So that's part 1A. We've now reasons about entailment. I hope you enjoyed it as much as I did. Next, we'll go to part 1B. So we have this sentence: food implies party, or drinks implies party, implies food and drinks implies party. So determine using an enumeration whether this sentence is valid, satisfiable, but not valid, or unsatisfiable. So just to remind ourselves, valid, what that means is it's true in all worlds. Satisfiable, but not valid. So satisfiable just means it's true in any world. And unsatisfiable means false in all worlds. So using an enumeration means that we're going to do a truth table. So let's just draw the truth table. So I'll draw it on this in this free space underneath. So let's say this is the value of food, and this is the value of drinks, and this is the value of party. And we want to figure out, is it the case that food implies party, or drinks implies party, implies food, or food and drinks implies party, big brackets around these. So the way I'm going to figure this out is I'm going to have a few of these expressions sort of separated out. So let's make these food, drinks, party. That's a D, not a P. Party. No. Right. First, we're going to have a column for food implies party. Column for drinks implies party. And a column for food and drinks implies party. And another column for our statement, which is the thing that I'll just put above because it's kind of big. All right, so let's get to it. So we're just going to draw rows for all of the possible combinations for food, drinks, and party. So the way I do this is party. It could be true, false, true, false. There are 8 possible worlds because like 2 values for food, 2 values for drink, 2 values for party. 2 by 2 is 8. So I'm going to draw 8 rows. So I'm going to alternate party each row: true, false, true, false, true, false, true, false. I'm going to alternate every 2 for drinks. So true, true, false, false, true, true, false, false. And I'm going to alternate every 4 for food. So true, 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 false, 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 false. And actually, to make this a bit more readable, I'm going to do these in different colors. So this is going to be in red, which I'll remind here. And drinks implies party is going to be in green, which I'll do here, this green. And food and drinks implies party, that's going to be in blue. Blue is a nice color. RGB. Style. No, blue is what I chose. Okay, so food implies party. Well, food is true and party is truth, and food implies party is true. The only way food implies party can be false is if food is true and party is false. So it's false in this row because it's false in this row because food is true and party is false. And here, food is also true and party is also false. But everywhere else, it's true. Like these are the only two ways to falsify food implies party. Now, drinks implies party. That's only false in the worlds where drinks is true and party is false. So this one and this one, right? So false here, true, 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 true. Okay, I'll delete those. Now, food and drinks implies party. The only way that could be false is when you have food and drinks, but you don't have party. So where do you have food and drinks, but you don't have party? Here. And that's the only place where you have food and drinks, but not party. So it's false here. But true, 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 true. Now the question is this big implication here. So the only way this can be false is when you do have this. So this part is true, and this part is false. So let's look at the places where food implies party or drinks implies party. So that's this row, that's this row, that's this row, this row. Yeah, basically all the rows except this one where both were false. So in this one where both were false, our statement is just false. Or no, our statement is true, sorry. A implies B is always true if A is false. Now in all the ones where it's true, we need to check if food or drinks implies party is true. But we can see that it is actually true in all of them. So our statement is true, 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 true. So our statement is true in all the possible worlds. And what that means is that this sentence is valid. All right. That was kind of tedious, but had to be done. Sorry about how boring it was. I'll move this truth table down a little bit and shrink it as we get to our next question, which is convert the left hand and right hand sides of the main implication into CNF. So again, this is gonna, here we're gonna need to use some space. So what's the left-hand side of the main implication? So let's remind ourselves the main implication is food implies party or drinks implies party. All that implies that food and drinks implies party. Okay, so let's convert the left-hand side into CNF. So food implies party or drinks implies party. Well, the first thing you do is you get rid of these implies symbols, right? That's, CNF, it's got like ands, ors, and nots. It doesn't have any of these. So the thing to remember is that X implies Y is exactly the same thing as not X or Y. So food implies party. We can replace that by not food or party. And drinks implies party. We can replace that by not drinks or party. So what do we do next? Well, we can kind of get rid of these, get rid of the brackets, right? Because we've just got the or of a bunch of different things, right? The next thing we can do is we can rearrange a little bit. So this not drinks, we can swap it with the party here, because like or A or B is the same thing as B or A. And now party or party, right? This thing, that's just exactly the same thing as party, because if party is true, then party or party is true. If party is false, then party or party is false. So same thing. You can get rid of this. And so the left-hand side is not food or not drink or party. What about the right-hand side? I'll do that in red this time. So that's food and drinks implies party. And so again, we've got to get rid of this implication here using this rule right here. So that's the same thing as not foods and drinks, or party. So now we've got to put this not inside. So not foods and drinks. Well, you add a not to the food, turn the and into an or, and you add a not to the drinks. So what this is, and I'll put a bracket around these, not food or not drink or party. But now, because we have a bunch of ors together, we don't really need to keep track of which goes first. So it's not food or not drink or party. So we've done it. We've converted the left-hand side and the right-hand side of the main implication into CNF. I'll just put a big tick there. Now, the next question is, I'll again shrink this, move it there. What do you observe about the left-hand side and the right-hand side after converting to CNF? Explain how your results provide the answer to part B1. Well, let's look at them a little bit more closely, right? This is the left-hand side, this is the right-hand side. And they look pretty different because one's written in black and one's written in red. But, obviously, if you think about it, they're the same, right? Not food or not drink or party. I'll draw a big three line equals. They're just the same statement. So how does that prove the answer to part BI? Well, part BI was whether the sentence was valid, satisfiable, or unsatisfiable. Well, because the thing before the implies was the same thing as the thing after implies. This whole thing is basically like alpha implies alpha for a complicated alpha. For alpha is, not foods or not drinks or party. It's just the same thing. So, pardon me. It's fine. I don't have the Rona. So alpha implies alpha. That's just true, right? So that's how we can use conjunctive normal form to, instead of doing this like whole tedious thing with this truth table, we can just manipulate some expressions and then check that they're the same thing, and our life is just so much easier. All right. So now we're moving on. We're going to the encrypted knowledge base. Oh man, isn't this exciting? So we have a propositional logic knowledge base, as shown below, and we're trying to find a satisfying assignment for the variables A, B, C, D, and E. Each line is a valid propositional logic sentence. So we have not A, we have B implies A, we have D, we have C or B, and we have D or E. So our buddy Albert, who is a cool guy, he runs the solver and he hands you a model. So in our model M, A is false, B is false, C is true, D is true, E is true. And in this one, all of our knowledge-based sentences are true, right? A is false, boom. B is false. Well, if B is false, B implies A is true. D is true, great. C or B, well, C is true, so we have that. And D or E, well, E is true, so we have that. So all of our things are true in this model. And we have a query sentence, alpha. So alpha is A or C implies E, right? Let's highlight that. Yeah, alpha is A or C implies E. In our model, alpha is also true, right? Because that's not what I want. So A or C implies E. Well, in our model, E is true. So if E is true, then A or C implies E has got to be true. So in our model, alpha is true. Can we say that the knowledge base entails alpha? Explain briefly in one sentence why or why not. And the answer is we cannot. Because remember, entailment is about all the possible worlds. Do I still have this picture? Well, I'll draw it again. This is all the worlds. We needed it to be the case that like this is beta and this smaller thing is alpha. That's the only case in which alpha entails beta, right? So you need to look at all the possible worlds. So are there any models for which the knowledge base can be true and the query can be false? Well, if you think about it for a while, you'll find out that if you have A is false, B is false, C is true, D is true, and E is false. that satisfies the knowledge base, right? All of those are going to pass, but your sentence is going to fail. So yeah, the knowledge base does not entail alpha. And you've just got to remember that entailment is about all the possible models or all the possible worlds. All right, so now we're going to attempt to use theorem proving methods to see whether our knowledge base entails a query sentence. To use these methods, it's useful to convert our knowledge base to conjunctive normal form, CNF. The sentence is a conjunction of clauses. Each clause is a disjunction of literals. Oh yeah, one thing, just to make this like very explicit, conjunction means and disjunction means or. And each literal is a symbol or a negated symbol. Okay, so which sentences in the knowledge base are not already in conjunctive normal form? Convert them to CNF. Okay, so let's look at this knowledge base a little bit more closely. So is alpha in CNF? The answer is yes. It's just a negation of a single thing, so that's fine. Is beta implies alpha in CNF? No, we can't have implies symbols in CNF. So what we do instead is we remember that beta implies alpha is the same thing as, sorry, B and A. B implies A is the same thing as not B or A. So now it's the conjunction of a bunch of clauses, specifically one clause, right? It's just the and of one thing, so you don't ever write an and. That's how we think about it. We're kind of weird here. And you've got an or, so that's fine, and you've got not B is fine, A is fine, so this is now in CNF. Right, D, yeah, there are no ands, there are no ors, it's totally fine. You've just got a little symbol, C or B, just got an or, that's fine. D or E, just got an or, that's also fine. So the only thing we had to do is this thing right here. B implies A got turned into not B or A. All right, so let's write the entire knowledge base as a single sentence in CNF, not just for fun, but because that's the next thing on it. So the thing we're going to do is, the thing about conjunctive normal form is just, it's like the and of a bunch of things. So if you have a list of things that are in CNF, you can just and all of them together, right? So, and then that will also be in CNF. So we can just write not A and B implies A, but we can't write B implies A. We've got to write not B or A, and D, and C or B, and D or E. Oh, I was supposed to do that here. Hopefully I won't lose marks on this worksheet. All right, so yeah, we just took the conjunction of all of the sentences, and that's a single sentence in conjunctive normal form. A thing to note is you've got a bunch of ors, sorry, a bunch of ands. These are ands. Sorry, these are ands. And the ors are like on the insides of the brackets. All right, so next we've got a new question. We have A and B or C and D, and we want to convert that to CNF. So how do we do that? So we're going to have to remember a very special rule. So that is that alpha or beta and gamma. So this is the case where we have like the or of things, like the or of an and, right? Here, the or is on the outside and the and is on the inside. That's like the reverse of what we had. So how do you like flip those around? And the answer is that this is just the same thing as alpha or beta and that's not an alpha. Alpha or gamma. And you can check that with truth tables if you want. This is just, these are true in the same worlds, so we can just replace them. True, these are the same in all of the worlds. All right, so here's our rule that we're gonna put off to the side, or we're gonna keep it there. So now we're gonna take our A and B, or C and D. And what we're going to do is we're going to think of the A and B as one thing. It's going to be our alpha. We're going to think of C as our beta, and we're going to think of D as our gamma. Purple. All right. And all right. So this is what we're converting to CNF, and we can just use this rule. So what we get is A and B, or C. So all of that, and A and B, or D. Right? That we just treated A and B as alpha, C as beta, and D as gamma. So, all right, now that we understand how that worked, I can just make all of these in a boring black style, because now we have that and or thing that we've got to do again, right? We've got to apply it to this one here and this one here, where we sort of, you can think of it as C or A and B. So C is alpha and B is this one, and similarly to the D. So if we do that on both sides, what we get is we get A or C and B or C and A or D and C or D. So I just did the same thing on all the sides. Now, and is associative, so that means it doesn't matter how you group them. So these outside brackets here, we need that bracket, but these ones we don't really need. It's A or C and B or C and A or D and C or D. So this is CNF, right? The ORs are, sorry, keep getting this wrong. The ORs are here on the ANDs. The ANDs are here on the outside, and the ORs are here on the inside. And that's just what CNF is. All right, so we are done with today's worksheet. I hope you enjoyed it, and I'll talk to you again next week. Goodbye.